Okay, here's our second equilibrium example. We have figure 12-6a shows a safe of mass big M equals 430 kilograms hanging by a rope of negligible mass from a boom. A equals 1.9 meters and B equals 2.5 meters. They're telling us these lengths here. This is 2.5 meters and this right here is 1.9 meters. That consists of a uniform hinged beam, mass of 85 kilograms. So that means the beam is what weighs 85 kilograms, and a horizontal cable of negligible mass. A, what is the tension in the cable? In other words, what is the magnitude of the force TC on the beam from the cable? And then B, what is the magnitude of force F of the net force on the beam from the hinge? So here again, we are at static equilibrium, which means that the net force on the object has to equal 0 and the net torque on the object has to equal 0. So first and foremost, since we want to find the tension in the cable for part A, we're going to have to draw all the forces and then see what we have to do to find that tension. So our forces here, if I draw them out, we have acting on this point right here, I have that tension force. So tension in the cable, which is what we're searching for here. I have the force of gravity from that hanging object, which we called a safe. So force of gravity of the safe there. And then we also have the force of gravity from the beam because the beam does have a mass. So force of gravity from the beam is going to come from the center of mass. So that force of gravity of the beam goes there. Now, on that hinge, we also have a vertical force, so we'll call that FV, and we have a horizontal force, FH, on the actual hinge part. So what we're going to do here is we can see that we don't know, we want to know the tension in the cable. We know the mass of the safe and we know the mass of the beam. So the force of gravity of the safe and force of gravity of the beam we can find. So we're not really worried about those things, but we don't know the vertical force on the hinge or the horizontal force on the hinge. So if we use that the net torque is equal to 0 and we put our axis of rotation at that hinge right there, because those two forces are at the axis of rotation, they're not going to provide any torque on the beam because, again, that moment arm is 0 because R equals 0 when you're at the actual axis of rotation. Remember, R in that torque equation is equal to the distance from the axis of rotation to where the force is acting. So here, R equals 0 for both FV and FH. So therefore, I don't need to know what those things are. Okay, so for part A, we are going to use net torque is equal to 0 for that part. Now let's see what direction those torques are going to be. So we can see that, okay, the force of gravity of the beam, that's going to pull clockwise direction. So that's going to be a negative torque. Force of gravity of the safe is also going to pull clockwise. So that's going to be a negative torque. And then we can see that that tension force is going to pull counterclockwise. So that's going to be a positive torque. So now we can plug those signs in. So our 0, our net torque, is equal to a positive torque from the tension minus the torque from the beam minus the torque from the safe. Okay. Now, we know that torque is equal to RF sine theta. Now, there's a couple of different ways to do this. We can find the angle here, that theta right there. We could find that if we want to. We also can use the perpendicular moment arm component and just say sine of 90. And what I mean by this is I know that that tension in the cable right here, if I look at this force right here, the perpendicular R vector to that force is this 1.9 meters right there. So if I just take that force and add it to this point right here, it's going to cause the same amount of torque on that axis of rotation, but now my angle is 90 degrees and I can kind of drop that sine of 90 because sine of 90 is just 1. Okay, and you can do that to any of these forces right here. It just makes the calculation a little bit simpler. So what we're going to do here is we're going to use our perpendicular R components and then just drop that sine of the angle. So torque is equal to R perpendicular times the force. So here for my tension, we get 0 is equal to R perpendicular, which is that 1.9 meters for tension, times the force of tension. So minus, and then again, I'm going to do this in a different color so you can kind of see what's happening here. The torque from the beam, and we can see that this beam is acting here, which is in the very center of that beam. And I know that this distance across is 2.5 meters. So what that means is that the distance from that perpendicular distance from the hinge or the axis of rotation to where the beam is acting is going to be 2.5 divided by 2. Or 1.25. All right, so this is going to be 1.25 for our beam. Our perpendicular is 1.25 times the force of gravity of the beam. And then for our safe, that distance from the axis of rotation to the safe is that 2.5 meters. So that's going to be our R perpendicular for the safe times the force of gravity of the safe. All right, so plugging in our numbers here, we get 0 is equal to our perpendicular for the tension force, which is a 1.9 meters, times the force of tension, which is what we're trying to find, minus the R perpendicular moment arm for the force of gravity of the beam, which was 1.25 meters, times the mass of the beam, which they give to us was 85 kilograms right there, times 9.8 meters per second squared. And then minus the perpendicular R vector or moment arm for the safe, which was 2.5 meters, times the force of gravity of the safe, which was the mass of the safe, 430 kilograms, times 9.8 meters per second squared. So here we get 1.9 times force of tension minus 1.25 times 85 times 9.8, which is 1,041.25 minus 2.5 times 430 times 9.8, which is 10,535. Those are both newtons. Okay, so, adding those to both sides, we end up getting 11,576.25 equals 1.9 times force of tension. Dividing this by 1.9, we get that the force tension in the cable is equal to 6,092.76 newtons. So that's our answer for the force of tension for part A. And then for part B, it says find the magnitude F of the net force on the beam from the hinge. So net force on the beam from the hinge, we have to find both the vertical force and the horizontal force. And then we have to use Pythagorean theorem for both. Now I'm going to erase all these crazy vectors that I've drawn here just so that we can see what's happening now. Oh no, I erased all my stuff. Whoops. Okay. Okay, so we have force of gravity of the beam, horizontal force. What else did I erase? Tension force. Okay, tension in the cable. Okay, so in order to find the vertical force and the horizontal force, we want to look at all the forces in the horizontal direction, all the forces in the vertical direction. So because we're at equilibrium, net force is equal to 0. Now this means both net force horizontal is equal to 0, and then separately net force vertical is equal to 0. So let's look at horizontal forces first because we only have 2 of them. We have the force horizontal from that axis of rotation or the wall, right? on the beam. And then we also have the tension in the cable. So we can see that these are faced opposite directions, which means that they have to be equal to each other in order for our net force horizontal to be equal to 0. All right, so for letter B, we have net force in the x direction, or the horizontal direction, equals 0. And then here I can say that right is positive, so that would mean that force horizontal, so 0 equals force horizontal minus that tension force. And so therefore horizontal force equals the tension force, which of course is just a proof of what I just said. Now we just got the tension force that equals 6,092.76 newtons. So we already have the horizontal force, that's easy. And then net force in the y direction, or the vertical direction, is also equal to 0. So looking at the vertical forces, let's do this in green. I have the vertical force on the wall up right there. So that's going to be my positive force. So I have F vertical. 0 equals F vertical, and then minus the force of gravity on the beam minus the force of gravity on the safe. And again, those are negative because they're pointing downward. I said up was positive. So here I'm solving for force vertical. So that's just going to equal force of gravity on the beam plus force of gravity on the safe. Plugging in our numbers, we get mass of the beam was 85 kilograms times 9.8 meters per second squared, plus mass of the safe was 430 kilograms times 9.8 meters per second squared. So our vertical force is equal to 5,047 newtons. And then now we have both the horizontal force and the vertical force, and we can find the overall force on, that was part B, find the magnitude F of the net force on the beam from the hinge. So the magnitude of the net force on the beam from the hinge is going to be the square root of the horizontal force, which is at 6,092.76 squared plus 5,047 squared. And so we end up getting, square that, plus 6,092.76 squared, and then take the square root. We end up getting the net force on the beam from the hinge is 7,911.63 newtons. So that's our answer for B. And they only asked for the magnitude of the net force, so that's all we have to do for letter B.